Electrical heating system. A physics student has an assignment to make an electrical heating system with the set of materials shown. The battery has an EMF of 12 volts and an internal resistance of 0.5 ohms. Each heating coil has a resistance of 17.3 ohms. So here's the heating coils, and what do they look like? They look like resistors, don't they? It's something called resistive heating. You pass current through a resistor and it heats up. So that's why it looks like a resistor. So here's our givens up here. The EMF is 12 volts, the internal resistance of the power source is 0.5 ohms, and the resistance of each heating coil is 17.3 ohms. So first, draw a diagram showing all the elements connected in one electrical circuit that produces the maximum rate of heat, which means power. Rate of heat, right? That's heat per time, that's power, energy per time. Use 2 meters in your circuit that will enable you to measure the power supplied by the battery. The switch is closed. What is the current through the battery? What is the terminal voltage of the battery? And then what is the rate of energy, which is the energy per unit time, otherwise known as power, delivered by the heating system? The switch is closed for 5 minutes. What is the total energy dissipated in the heating coils? So first, draw the diagram. But before we draw it, we have to plan it. So here's a couple facts that will help us. The battery EMF remains constant. That does not change. The power supplied by the battery to the heating coils will be the voltage through the coils squared divided by the resistance of the coils. The voltage in the coils is supplied by the battery. Now, as the current increases, the voltage supplied by the battery will decrease a little because, why? The battery has an internal resistance. But that's a small effect, as the internal resistance is much smaller than the coil resistance, right? It's about 34 times as small. To maximize the power delivered to the coils, we're assuming that this voltage stays pretty much constant across the coils. The net resistance of the coil should be a minimum. The resistance is in the denominator here, so if we can make this small, the power delivered to the coils goes up. We have 2 heating coils that we can use. Each one has a resistance of 17.3 ohms. We want to minimize their net resistance. That means they should be attached in parallel, so let's prove that. So if we put the 2 coils in parallel, we use this equation, and we get 1 over 17.3 plus 1 over 17.3, add them, flip them, and we get a net resistance of 8.65. To check that, to make sure it makes sense, is whenever you put resistors in parallel, their equivalent resistance will always be less than the smallest resistor you have in parallel. So is 8.65 less than 17.3? Yep, so that kind of checks. Doesn't prove it, but at least shows we're on the right track. If we put them in series, well, you just add the resistances. So you get 34.6, which is large compared to this one. So we're going to hook up our heating coils in parallel. Here's our circuit. The heating coils are connected in parallel. That will minimize their resistance and maximize their dissipated power. And then you can see the current now comes out of the battery, splits, goes to each coil in parallel, and comes down this way. The ammeter is connected in series with the battery to correctly measure the current. And hang on, let me just erase this so you can clearly see it. Here's your ammeter in series. That'll measure the current coming out of the battery. We connect the voltmeter in parallel with the coils to measure their voltage. Remember, ammeters always in series with what you want to measure, and voltmeters always in parallel. The switch is closed. What is the current through the battery? We need to find the equivalent resistance of the entire circuit. So what is that going to be? Well, we have the equivalent resistance of these 2 coils here, right? They're just resistors, and that is 8.65. What other resistance do we have? We've got this internal resistance of the battery, which is a virtual resistance. It's not a real resistor, but it acts like one. So we have actually a series circuit now of the internal resistance, the R equivalent here for our heating coils, and then we go back to the battery. So the current will be the EMF, that's this thing right here inside the battery, divided by R equivalent. And that's equal to, R equivalent will be the internal resistance plus the external resistance, which is this one up here. So it's 12 volts over 0.5 plus 8.65 ohms, and the current is 1.31 amps. What is the terminal voltage of the battery? Our equation for terminal voltage is EMF minus I times R, where I is the current in the circuit. So the EMF here is supplying 12 volts, but the battery is a little old. It has some internal resistance. Not all of that voltage is applied to our heating coils. There's a slight voltage drop here inside the battery. And then when you measure that, you measure it here in parallel. If you'd like to measure that, we don't have to. We're more interested over here. So the terminal voltage is EMF minus IR. Here's the EMF, 12 volts. Here's the current going through our circuit. Here's your internal resistance. So the voltage supplied by the battery to the heating coils is not the 12 volts, it's only 11.35. But that does validate our earlier claim that the terminal voltage is not that different from the EMF. What is the rate of energy? And whenever you see this phrase, that means energy over time, which is power, delivered by the heating system. We're going to use the power equation, V squared over R, with the net resistance of the heating coils and the terminal voltage, not the EMF. Only the terminal voltage is applied to the heating coils. So here's our equation, V terminal squared over R net, 11.35 volts squared, make sure you square it, divided by the resistance of the two heating coils, which is 8.65 ohms, and we get 14.9 watts. The switch is closed for 5 minutes. What is the total energy dissipated in the heating coils? Actually, what does this mean? What's going on to the energy? Well, you have the electrical energy of the current, and it's heating up the resistor. So what is happening there is that electrical energy is being transformed into heat, thermal energy. So now our equation, power is energy over time. We want to find the total amount of energy, so that's power times time. Here's our power. We have 5 minutes, but can't use 5 minutes, have to convert that to seconds. 1 minute is 60 seconds, and we get 4,470 joules.